Okay, we were talking about section 7.1, differential equations. It's really an introduction to differential equations. And we covered a few examples, and here's another example. Let me give you a moment to copy it down. Okay, so, all right, what we have here, of course, is a differential equation. Here it is. And why is this a DE class? DE stands for differential equation. Why is that a differential equation? It's an equation, but they're calling this equation a differential equation. That's right, Renaud, the y prime. Very good. The equation has a derivative in it. Now, it turns out that differential equations have what's called a family. They can have what's called a family of solutions. Why are they calling this? Why are they calling this here? Why are they calling this a family of solutions?
How constant is C?
That's right. Good, Leping. There's a constant C here. There's a constant C. So that constant could be any constant, and that means that there's an infinite number of solutions. Now, all the solutions have a log of x and an x in it, but that constant could be any constant. All right. Now, what we want to do then is, after we want to show that this is a member, that every member of the family solutions is, or every member of this family of functions here is a solution of the differential equation. And then after that, we're going to find a solution that satisfies as what we call an initial condition. What this initial condition means here is that when x equals 2, y equals 1. But this is now separate, a separate question from the first question. First question is show that every member of this family of functions is a solution to the differential equation. How would I show that? How would I show that? Well, let's take an analogy. Let's say I have 2x plus 3 equals 11. Okay, and let's say that somebody says to you, that, hey, x equals 4 is a solution to this equation here. Okay, what's going to make you believe that? How are you going to confirm that x equals 4 is a solution to this equation here? Samuel?
Solve for x.
Well, let's say we don't know algebra. That's a very good point what you said. You could use algebra and solve for x. That is one way. But let's say, I mean, it's kind of, we know algebra, right? But let's say that that maybe you don't know a whole lot of algebra. Okay, how else could you confirm that x equals 4 is a solution to this equation?
Plug it in.
Plug in x.
Plug it in. That's right, Maria. Plug it in. Okay, well, all right. Let's see. So 2 times 4 plus 3 equals 11. Yep. 11 equals 11. Yep, that's right. So we can do the same thing for our differential equation. We can plug in this family of solutions and see if it satisfies the differential equation. Okay, are there any questions on that before we move on to do that? Marcus?
Yeah, so I stepped out for a second, so I didn't see how you got the equation, but I'm assuming you plugged in the numbers, right? X equals 2, y equals 1.
Well, no. Well, we haven't really done anything yet. All we're doing, later on, certainly next week, you're going to learn, given a differential equation, you're going to learn a way to solve a certain kind of differential equation. But right now, all you're being asked to do is to see if this family of solutions is a solution, or family of functions is a solution to this differential equation. And to do that, all we need to do is plug the family of functions, plug the solution in, or plug the y in for y in the differential equation, and see if it's true. Let me show you. So first of all, here's ry, and I know that the differential equation has a derivative in it, so I'm going to find the derivative of y using the, what rule is this here?
Division rule.
That's the quotient rule, right? So Okay. Let me just see here. Right. So I have here, you know, I have F over G. And so here I have F prime times G minus F times G prime all over G squared, right, on the bottom there. And so this is what Y prime is. That's my derivative. Now what I'm going to do is I'm going to substitute that derivative in the left side of the differential equation. You know, I'm not saying yet that this equals 1. I'm not saying that yet. Okay, I'm not saying that yet. I'm going to substitute in the y for the y and the y prime. I'm substituting in what I think y is and what y prime is. And when we work it out, we get the left-hand side equals 1. Therefore, this family of solutions, this is a family of solutions to my DE differential equation. Let me give you a moment to you know, copy that, and please let me know if you have any questions. Okay, all right. So it's absolutely amazing that a differential equation can have really an infinite number of solutions, because this constant C can be any constant. All right. As a matter of fact, let me just check one thing here. One moment, class. One moment here. Yeah, that's fine. That's fine. So, a family of solutions. Now, if we were to specify a point at which we want our solution to pass through, then we would be solving what's called an initial value problem. Okay, let me show you this on the next page. I assume we're all good here, right? Okay. If we require that y of 2 equals 1, another way of saying that is the solution must pass let me do this better here. Okay, this means the solution must pass through, I'll do it vertically, must pass through the point 2, 1. I mean, we can graph a function, but now what we're doing is we want our, of this family of solutions, we want our solution, we're adding what's called an initial condition. We want our solution to pass through the point 2, 1. So this means when y equals 1, x equals 2. And we can find then a specific value for the constant. And so the solution to the initial value, when we determine that the constant is 2 minus the log of 2. Now that's for the solution that passes through the point 2, 1. If we were to specify another initial condition, do you think we'd get a different constant? If we had a different initial condition, do you think we'd have a different
Yes.
constant? We would. Absolutely. And so, okay, we've solved our initial value problem. Okay, please let me know if you have any questions on that. Okay, well, this is really then what section, I mean, this gives you an idea of section 7.1. And what we're going to do is we're going to move now into section 7.2. Okay, you know, before I do that, everybody's comfortable? Okay, give me a thumbs up if you have the example copied. And all right, Nicole's good, Tall's good. Okay, very good, very good. All right, I'll stop the recording. Okay, very good, thank you.